NENOMATICA, where mathematics meets YouTube excellence. For every a greater than 0 and a not equal to 1, f of log base of x equals 0 is equivalent to the system where log base of x equals t1 or t2, and so on up to tn, where t1 through tn are the roots of the equation f of t equals 0. The algorithm is powered by a simple substitution. Let t equal log base a of x. Then you first solve the simpler algebraic equation, f of t equals 0. Next, for every root ti, solve log base of x equals t, I to get x equals a to the power ti. Now, let's follow the algorithm on a concrete example. Solve the equation. Open parenthesis, log base 2 of x, close parenthesis, squared minus 5 times log base 2 of x plus 6 equals 0. Step 1. Let t equal log base 2 of x. Then our equation becomes a simple quadratic in t. Step 2. Solve f of t equals 0. The quadratic factors as open parenthesis t minus 2 close parenthesis times open parenthesis t minus 3 close parenthesis equals 0. So the roots are t1 equals 2 and t2 equals 3. Step 3. Return to x by replacing t with log base 2 of x in each root. That gives the system log base 2 of x equals 2 or log base 2 of x equals 3. Step 4. Convert each to exponential form. From log base 2 of x equals 2, we get x equals 2 squared, which is 4. From log base 2 of x equals 3, we get x equals 2 cubed, which is 8. Example. We will solve the equation 26 to the log x minus 24 to the log x equals x. Throughout, log means base 10. Step 1. Perform a substitution. If log x equals n, then x equals 10 to the n. This lets us express every term with the same exponent, n. Step 2. Rewrite the equation using n. 26 to the n minus 24 to the n equals 10 to the n. Step 3. Isolate the largest power term. So 26 to the n equals 24 to the n plus 10 to the n. Step 4. Divide both sides by 26 to the n. That gives 1 equals quantity 24 over 26 to the n plus quantity 10 over 26 to the n. Step 5. Simplify the fractions. 1 equals quantity 12 over 13 to the n plus quantity 5 over 13 to the n. Now notice a familiar 5, 12, 13, right triangle. If sine alpha equals 5 over 13, then cosine alpha equals 12 over 13. Step 6. Rewrite using cosine alpha and sine alpha. 1 equals cosine to the n alpha plus sine to the n alpha. Step 7. By the Pythagorean identity, cosine squared plus sine squared equals 1. Therefore, this equality holds when n equals 2. So n equals 2 semicolon x equals 10 to the n. Step 8. Substitute 2 for n. X equals 10 squared. Step 9. Compute the value. X equals 100. Finally, state the solution set. D equals the set containing 100. Therefore, the solution is x equals 100. Set containing 100. Therefore, the solution is x equals 100. Example. We will solve the equation log base cosine x of sine x plus log base sine x of cosine x equals 2. Step 1. Determine the domain where both logarithms are defined. Arguments must be positive, bases must be positive, and bases cannot be 1. For this equation, sine x must be greater than 0 and cosine x must be greater than 0. That places x in the first quadrant only between 2k pi and 2k pi plus pi over 2. Step 2. Use the reciprocal property for logarithms. Log base b of a equals 1 divided by log base a of b. That lets us rewrite the second term. Step 3. Let t equal log base cosine x of sine x. Then the equation becomes t plus 1 over t equals 2. Step 4. Multiply both sides by t and move everything to one side. We obtain t squared minus 2t plus 1 equals 0. Step 5. This is a perfect square. Therefore, t equals 1. Step 6. Substitute back for t. log base cosine x of sine x equals 1, which means sine x equals cosine x to the first power. Dividing both sides by cosine x gives tangent x equals 1. Step 7. The general solution of tangent x equals 1 is x equals k pi plus pi over 4, where k is any integer. Step 8. From our domain, x must lie in the first quadrant, so we keep only the angles of the form 2k pi plus pi over 4. Therefore, the solution set is the set of all x equal to 2k pi plus pi over 4. We will also write the domain conditions under which every logarithm is well defined. Step 1. Apply the power rule to the left exponent and expand the right side using the property that the logarithm of alpha times c equals 1 plus the logarithm base alpha of c. Step 2. Introduce substitutions to simplify. Let capital A equal log base alpha of c, and let y equal log base alpha of x. Step 3. Use the identity a to the log base c of b equals b to the log base c of a to rewrite the first power. Then set z equal y to the power log base b of a. Step 4. Move all terms to one side to form a standard quadratic and factor it. Case 1. Let z equal 1. Then y to the power log base b of a equals 1. Take log base b of both sides. That gives log base b of a times log base b of y equals 0. Therefore, log base b of y equals 0, so y equals 1. Then log base alpha of x equals 1 equals 1. Take log base b of both sides. That gives log base b of a times log base b of y equals 0. Therefore, log base b of y equals 0, so y equals 1. Then log base alpha of x equals 1, and x equals alpha. Case 2. Let z equal a. Then y to the power log base b of a equals a. Take log base b of both sides. We obtain log base b of a times log base b of y equals log base b of a. Hence, either log base b of a equals 0, which implies a equals 1, and therefore c equals alpha, or log base b of y equals 1, which implies y equals b, and log base alpha of x equals b, so x equals alpha to the b. Therefore, the solution set for x matches the given outline exactly. Recap. We used the power rule, expanded the right-hand side into 1 plus log term, substituted a and y, applied the exponent change of base identity, turned the equation into a quadratic in z, and solved two simple cases to get x equals alpha or x equals alpha to the b. Example. In this lesson, we will solve, step by step, the logarithmic equation log base 2 of the quantity 1 plus the square root of x equals log base 3 of x. We will follow a fixed algorithm and show every step on screen. Step 1. Define the substitution. Let y equal log base 3 of x. Then, by the definition of a logarithm, x equals 3 to the y. Step 2. Substitute into the original equation. Start from the original equation. Replace x by 3 to the y and log base 3 of x by y. This simplifies to log base 2 of 1 plus the square root of 3 to the y equals y. Step 3. Convert the logarithm to exponential form. 1 plus the square root of 3 to the y equals 2 to the y. Rewrite the square root. The square root of 3 to the y equals the square root of 3 all to the y. Step 4. Divide both sides by 2 to the y. We obtain left parenthesis 1/2 right parenthesis to the y plus left parenthesis the square root of 3 over 2 right parenthesis to the y equals 1. Step 5. Recognize familiar trigonometric values. Sine of pi over 6 equals 1/2, and cosine of pi over 6 equals square root of 3 over 2. Replace into the equation to get sine pi over 6 to the y plus cosine pi over 6 to the y equals 1. Let's visualize pi over 6 on the unit circle. Step 6. Determine the exponent y. The Pythagorean identity says sine squared theta plus cosine squared theta equals 1. Our equation matches this identity precisely when the exponent y equals 2. Therefore, y equals 2. Step 7. Back substitute to find x and check the domain. From x equals 3 to the y, substitute y equals 2 to get x equals 3 squared. Hence x equals 9. Domain check. Log base 3 of x requires x greater than 0, and the square root requires x at least 0. The value x equals 9 satisfies both, so the solution set is braces 9. To recap, define y as log base 3 of x, substitute, convert to exponential form, normalize, recognize the sine and cosine values for pi over 6, use the Pythagorean identity to get y equals 2, and finally compute x equals 9. Let's display the example and the domain restrictions. Step 1. Apply the power rule of logarithms to each term. Log base x over 2 of x squared becomes 2 times log base x over 2 of x. Log base 16x of x cubed becomes 3 times log base 16x of x. Log base 4x of the square root of x becomes 1/2 times log base 4x of x. Then rewrite the equation with those coefficients. Next, divide every term by 2 to keep the numbers small. Step 2. Use the reciprocal change of base identity. Log base I of b equals 1 over log base b of a. Apply it to each term to obtain a rational expression in logs with base x. Step 3. Expand each denominator using product and quotient rules. Log base x of x over 2 equals log base x of x minus log base x of 2, which is 1 minus log base x of 2. Log base x of 16x equals 1 plus 4 times log base x of 2. Log base x of 4x equals 1 plus 2 times log base x of 2. Substitute these into the equation. Step 4. To simplify the notation, let t equal log base x of 2. The equation becomes 1 over 1 minus t minus 21 over 1 plus 4t plus 10 over 1 plus 2t equals 0. Step 5. Combine the fractions over a common denominator and set the numerator equal to 0. Expand the numerator carefully. Combine like terms to get a quadratic in t. Step 6. Factor the quadratic. 2t squared plus 3t minus 2 equals 0 factors as t plus 2 times 2t minus 1 equals 0. Therefore, t equals negative 2, or t equals 1/2. Step 7. Substitute back t equals log base x of 2 to solve for x. If t equals negative 2, then log base x of 2 equals x. If t equals negative 2, then log base x of 2 equals negative 2. So log base 2 of x equals negative 1/2, which gives x equals 2 to the power negative 1/2. That is square root of 2 over 2. If t equals 1/2, then log base x of 2 equals 1/2. So log base 2 of x equals 2, which gives x equals 4. Finally, check the domain restrictions. Both values satisfy x greater than 0, and avoid the excluded values 1/16, 1/4, and 2. Therefore, the solution set is square root of 2 over 2 and 4. Example. Here is the problem statement. It consists of 2 equations and simple domain constraints. Step 1. State the domain. Both x and y must be positive and not equal to 1. Step 2. Use the change of base identity. Log base x of y equals 1 over log base y of x. Introduce the substitution t equals log base y of x. Replace log base x of y with 1 over t, and write the first equation in terms of t only. Step 3. Substitute t into the equation. We obtain t minus 1 over t equals 8/3. Step 4. Clear denominators by multiplying both sides by 3t. This yields the quadratic equation, 3t squared minus 8t minus 3 equals 0. Step 5. Solve the quadratic. It factors as 3t plus 1 times t minus 3 equals 0, so t equals negative 1/3, or t equals 3. Step 6. First case, t equals negative 1/3. Then log base y of x equals negative 1/3. Convert to exponential form x equals y to the power negative 1/3, which is 1 over the cube root of y. Substitute into x, y equals 16. That gives y to the 2/3 equals 16. So y equals 64 and x equals 1/4. Step 7. Second case, t equals 3. Then log base y of x equals 3, so x equals y cubed. Using x, y equals 16 gives y to the 4th equals 16. Hence y equals 2 and x equals 8. Final step. Collect both valid solutions. The solution set is the ordered pairs 8, 2 and 1/4, 64. The given condition is log base 20x of 22x equals log base 2x of 202x. We are asked to write the value of log base 20x of 22x in the form log base 10 of m over n, where m and n are natural and relatively prime, and then find m plus n. We first check the domain conditions for logarithms. Both bases must be positive and not equal to 1, and the arguments must be positive. Step 1. Set both equal logarithms to a single variable k. Then convert each logarithmic statement into its exponential form. Step 2. Divide the first exponential equation by the second to eliminate x. The left side becomes 22 over 202. The right side simplifies to the quantity 20x over 2x raised to the k, which is 10 to the k. Step 3. Rewrite 10 to the k as a logarithm to solve for k. Reduce the fraction 22 over 202 to lowest terms. Now match the format log base 10 of m over n and read off m and n. To recap, setting both logarithms equal to k and converting to exponentials allows the x to cancel cleanly when we divide. The resulting 10 to the k leads directly to a base 10 logarithm of a simple reduced fraction. Therefore, m plus n equals 112. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.